So let's talk about the theory behind NMR. We won't spend much time on this. We'll spend most of our time on reading and interpreting the NMR spectra. And so, right, NMR stands for nuclear, magnetic, resonance. And so the nuclear has not really much to do with nuclear chemistry. It's just because we're studying the nucleus of the atom. Magnetic, because we're going to use very strong superconducting magnets. And then resonance, this one's a little bit more tricky, but it said that these nuclei are resonating between two states. But yeah, we won't really go into that one too much. And so what we're doing is we're studying the nucleus of molecules, and some molecules will be NMR active and some will not. Our most popular example are going to be proton NMR, so H1 NMR, and carbon-13 NMR. You can, however, do other types of NMR, such as nitrogen, fluorine, phosphorus, and others. The requirement for NMR is you need an odd number of either protons or neutrons. And the reason that you need an odd number is because a nucleus has what's known as nuclear spin. And it's not really spinning, but it's somewhat spinning. And so what this does is it creates a magnetic field. And so we can talk about this magnetic field as an arrow, right? Kind of a north-south type of thing, or just as an arrow, right? And so under normal conditions, these spins can be facing whatever direction they want. And then what we're going to do is we're going to apply a magnetic field. It's going to be an extremely strong magnetic field coming from a superconducting magnet. And so we have a strong magnetic field that we call B0. And whenever we do that, our nuclei have one of two options. Either they can align with the magnetic field, or they can align against the magnetic field. Those are the two options. And naturally, as you might think, aligning with the magnetic field is going to be lower in energy than aligning against the magnetic field. And so now we've got this energy gap. So something we can do is we can shoot energy at it in the form of radio waves, right? And if we get the correct amount of energy, right, corresponding to this gap, our nuclei will go up into the spin up state or spin down state. And then after that, it'll relax back down. And when it relaxes back down, it's going to release some amount of energy. And that's what we measure. And so how big this energy gap is depends on how shielded your nuclei are. So what we say are that nuclei are shielded by electrons. And so, for example, if we take a look at methanol, and specifically here, we're going to take a look at the protons. So we're talking about proton NMR here. We have these three protons, and then we have this proton right here. If we think about what kind of atoms are near here, we have this oxygen atom, which is really going to pull these electron density away from this hydrogen. So this has low electron density, while these other hydrogens are just next to a carbon, and so they relatively have high electron density. And if you look at like the electrostatic potential map of methanol, which is what we have here, you can see that as well. You can see these three hydrogens are in this kind of green zone, They have plenty of electron density, and then this hydrogen over here is in this blue zone. It does not have as much electron density in it. And so we have our external magnetic field, and we have our electron with plenty, or our nuclei with plenty of electron density around it, represented by this kind of yellow highlighted cloud I made. And then we have our other nuclei that has much less electron density on it. And so we say this is shielded, and this is deshielded. And so the one with a lot of electron density doesn't feel the external magnet as much, right? Because it's shielded by all the electrons that are kind of floating on through here that are creating their own magnetic field and shielding the nuclei from this external magnetic field. And so since it doesn't feel this external magnetic field, when we shoot in our radio waves, this one is actually easier to excite to the higher energy level. So this one's relatively easy to flip from with the magnetic field to against the magnetic field, while the deshielded one feels the full external magnetic field. And so this one we say is kind of hard to flip. And so if we take a look at our NMR spectra, they actually go in the reverse order. We have 0 all the way on to the right, and then some number all the way to the left. And if we think about energy as our x-axis here, when we go from right to left, we increase the amount of energy. And so the shielded one will show up somewhere around here as a signal, and then the deshielded one will show up somewhere over here, right? This one is easy to flip, so it's low energy. We call this the shielded portion of our NMR, or we call this upfield. And then on this other side, we have the deshielded portion, or downfield. This is obviously, a very simple representation of NMR. It obviously is a lot more complex, but the main things that we want to kind of keep in mind is that we have this shielded region over here, which has a lot of electron density around our nuclei of study. And then we have this deshielded region right here, which does not have a lot of electron density around our nuclei of interest.